In electromagnetism, if we want to express Maxwell's equations in tensorial form, and then we need to introduce one form A, which is defined as minus phi dt plus ax dx plus ay dy plus az dz. Now, if we want to make the units of these coordinates to be same, then we introduce, instead of time, which has units of time, we introduce a new coordinate x0, which is c times t, where c is the velocity of light, so that now x0 has the same units as that of spatial coordinates, that is x0 has unit of length. We also use notation x1, x2 and x3 for spatial coordinates x, y, z, and we use notation a1, a2, a3 for ax, ay and az respectively. So with this new notation we can write, and we also introduce a0 as we define a0 as minus phi by c. So with this new notation we can write this one form a as a0 dx0 plus a1 dx1 plus a2 dx2 plus a3 dx3. And if we use Einstein's summation convention, then we can write it as a nu dx nu, with this repeated index nu is summed over. Now the electromagnetic field tensor F is defined as exterior derivative of A. If we use this expression here, instead of using Einstein's summation convention, if we use this expression and we calculate exterior derivative of A, then it is given by dA0 wedge product dx0 plus dA1 wedge product dx1 plus dA2 wedge dx2 plus dA3 wedge dx3. And in Einstein's summation convention we can write this as dA nu wedge dx nu. Now what is dA nu? dA nu can be written as del A nu del x0 dx0 plus del A nu del x1 dx1 plus del A nu del x2 dx2 plus del A nu del x3 dx3, and this whole thing is wedged with dx nu. Again, this expression in the brackets, we can write it using Einstein's summation convention as del A nu del x mu dx mu, and then we can wedge it with dx nu. Now since wedge is an antisymmetric product, so we can also write this expression as 1/2 del A nu del x mu minus del A mu del x nu and dx mu wedge dx nu. This expression here we call f mu nu. F mu nu dx mu wedge dx nu, where f mu nu is this expression here. So we have f mu nu equals 1/2 del A mu del x nu minus del A nu del x mu minus del A nu del x mu minus del A mu del x nu. Since this is antisymmetric, so when mu and nu are equal, then this will be 0, of course. But if, say, we take mu to be 0 and nu to be 1, then we get f(0, 1) equals 1/2 del A 1 del x 0 minus del A 0 del x 1, which is 1/2 del A 1 by del t with 1 by c minus a0 is 5 by c, so we have plus a0 is minus 5 by c, so del 5 by del x1 again with a factor of 1 by c. So this is equal to 1/2 times 1 by c and del 5 by del x1 plus del a1 by t, and this expression is nothing but the first x component of electric field, negative of the x component of electric field, divided by 2c. So f(0, 1) is minus 1/2 E1. Similarly, we have other expressions. For example, if we calculate all of these components, we can write f mu nu as a 2 by 2 matrix f mu nu 1/2 0th component is of course 0 because this is an antisymmetric tensor. First component f f01 is minus e1 by c as we calculated. F02 is minus e2 by c. F03 is minus e3 by c. F10 is e1 by c, then e2 by c, then e3 by c. F11 is 0. F12 is B3, third component of magnetic field. Then we have minus B2. Here we have minus B3, then 0. Then we have B1. Here we have B2, then minus B1, and then 0. So this is electromagnetic field tensor. It is a rank 2 covariant tensor. These are actually components of this tensor. So the actual tensor is this here: f mu nu dx mu h dx nu, and f mu nu. These are the components of this tensor.